How's it going, everybody? This is the first video from my machine learning playlist. In this video, we are going to learn what a logistic model is. It is a model that assigns a probability to a point in Rn, but this sounds very complicated, so instead of Rn, we will start by R, or the real line. This is the real line, or R, starting from negative infinity to positive infinity. For an arbitrary point x on the real line, the logistic model assigns a number between 0 and 1 to this point x. We call it model because it models the probability of points. The same thing is true for R2. For an arbitrary point here that has x and y, a logistic model assigns a probability between 0 and 1 to this point. Note that a logistic model is different than logistic regression. I will explain logistic regression in future videos. Now let's get into the details. To better understand a logistic model, we will start from R, or the real line. We all know what the real line is. It starts from negative infinity here to positive infinity here. I have an arrow here to denote the direction. As I explained, a logistic model assigns a probability to each point of the real line. In other words, a logistic model maps the real line to the closed interval between 0 and 1 here, where 0 is here and 1 is here. In other words, from this line, the real line, we want to get this closed interval. Intuitively, one can map endpoints of the real line to endpoints of this closed interval, meaning mapping negative infinity to 0 over here and mapping positive infinity to 1 over here. Also, we can force the middle point of the real line, which is 0 over here, gets mapped to the middle point of the closed interval, which is 1/2 here. Our goal is to take a point x on the real line and map it to the closed interval between 0 and 1 such that negative infinity gets mapped to 0, positive infinity gets mapped to 1, 0 on the real line gets mapped to the middle point of the closed interval, which is 1/2. All I explained is a description of a function whose domain is the real line and its range is the closed interval between 0 and 1. One choice is y equals f of x equals 1 over e to the negative x. Now let's see if it gets the job done. If you plug 0 in, you would get e to the 0 in the denominator and the ratio would be 1/2. If you plug positive infinity, you would get e to the negative infinity, which is 0, and then the ratio would be 1. And if you plug negative infinity, you would get e to the positive infinity, which is going to be infinity, and the ratio would be 0. Notice that the two last cases are limits and should be written in this form. The introduced function does the job and has a name and has a special symbol sigma for its representation. It is called a sigmoid function and is denoted by sigma of x. Its domain starts from negative infinity to positive infinity that covers all the real line. Also, its range is the closed interval from 0 to 1. Notice that at x equals 6, we almost get 1, and at x equals negative 6, we get 0. Also at x equals 0, we get 1/2, which it was desired. Now you may ask why the range should be the closed interval between 0 and 1. And the answer is that because any point on this interval can be thought as a probability of an event, that is why we force the range to be 0 to 1. Another question is that if there is anything special about mapping 0 on the real line to 1/2 on the closed interval, and the answer is no. We can map any point on the real line to 1/2 on the closed interval between 0 and 1. To elaborate on this, consider x equals 3. We can force 3 to get mapped to 1/2, but how? It suffices to substitute x minus 3 for x in the sigmoid function, and that's it. Take a closer look to see what else is going on here. We are mapping everything less than 3 here to something that is less than 1/2 here. and we are mapping everything greater than 3 here to something that is greater than 1/2 on the second half of the closed interval. In other words, we are partitioning the real line into two pieces, this piece and this piece, and we are mapping the first piece to the first piece of the closed interval and the second piece of the real line to the second piece of the closed interval. Now another question is that if I can do the reverse, I mean mapping numbers less than 3 over here to points greater than 1/2 here, and mapping numbers greater than 3 here to points less than 1/2 here. And of course, 3 here gets mapped to 1/2. The answer is yes, simply just like reversing the closed interval and writing it from 1 to 0, we can have a negative sign for x such that the term is 0 when x equals 3. There are two things we should be aware of. First, 3 here is an arbitrary number. It can be any number. Second, the sign of x in this argument tells us if the left-hand side gets mapped to the left-hand side or the right-hand side gets mapped to the right-hand side. This results into a formula on the next slide. Using this function, we can map the real line to the closed interval between 0 and 1, where x equals negative b over a gets mapped to 1/2. Also, if the sign of negative b over a is positive, then the left-hand side gets mapped to the left-hand side and vice versa. However, when the sign of negative b over a is negative, then the opposite side gets mapped to another one. What is the takeaway? The takeaway is that logistic model in R has at most two parameters A and B to partition R into two pieces, and each piece gets mapped to 1/2 of the closed interval between 0 and 1. Notice I mentioned that at most two parameters because the coefficient of x cannot be 0, therefore we have at most two parameters. So a logistic model in R is a function that has 3 arguments. 2 of them are a and b, and the last argument is x, whose probability is of interest. Well, next question to be answered is that if we can partition R2 into two disjoint pieces like what we did for R and assign probabilities to them. If so, how many parameters we need? Just draw a line in R2 and then you're done. The right-hand side of the line is one piece and the left-hand side of the line is the other piece. Like the real line, we can map each piece to each side of the closed interval between 0 and 1. For example, here we are mapping the right-hand side to the right-hand side of the closed interval and vice versa. Also, each point on the line gets mapped to 1/2. However, here the left-hand side of the line gets mapped to the right-hand side of the closed interval here. Now the question is how we can determine which side of the line should map to which side of the closed interval between 0 and 1. Suppose this line passes through 0, 2 here and negative 1, 0, so we can use this formula to get the equation of the line. Therefore, we have this formula, which is a very important formula because it is set to 0. We can replace this formula with x in a sigmoid function to get this formula. Now I am asking this question, which side of this line gets mapped to 0 to 1/2, and which side gets mapped to 1/2 to 1? Please pause the video and think about it. When negative 2x plus y minus 2 is greater than 0, all xy satisfying this get mapped to open interval 1/2 to closed interval 1. And when negative 2x plus y minus 2 is negative, they get mapped to the other half of the closed interval. And when we have negative 2x plus y minus 2 equals 0, every point gets mapped to 1/2. Therefore, we should be able to determine the sign of this equation. That is the answer, but let's see why. Pictorially, let x and y be 0, then the value of negative 2x plus y minus 2 equals negative 2. Therefore, the right-hand side is negative, and for all points on the right-hand side, this negative 2x plus y minus 2 is smaller than 0. Hence, we have a negative sign on the right-hand side, and the positive sign would be on the left-hand side. You may say that was a very tedious procedure. Is there an easier way to determine positive and negative sides? The answer is yes. Take this term as the negative exponent of E. Rewrite it as a vector product here. This right here is the transpose of the vector negative 2, 1. If you draw it, you would get this vector over here. Now, whatever side that the arrow is pointing towards is the positive side. So we have positive sign for all points on the left-hand side of the line. Remember that the line I picked was an arbitrary line. It can be any line. It can be this line, or it can be this line. No matter which line it is, we can model it as ax plus by plus c and rewrite it as a vector product. The vector AB determines if we are on the positive piece or negative piece. So we have this model for all x, y points in R2 as our logistic model. We have at most 3 parameters A, B, C, where A and B, the vector including A and B, has to be non-zero. Notice, like R, the logistic model is the composition of a linear term here and a sigmoid function. What is the takeaway? We derive this model as the logistic model in R2, which is a composition of this linear term and a sigmoid function. So for an arbitrary numbers for A, B, and C, this model assigns a probability to each point of R2. In other words, take this point that has X and Y. This logistic model assigns a number between 0 and 1 to this point. How about a basic model in R3? The same thing. Now we have at most 4 parameters A, B, C, and D. Using these 4 arbitrary parameters, we assign a probability to each point in R3. For example, take this point that has X, Y, and Z as its coordinates. We assign a probability to it using this logistic model. This one is a hyperplane in R3 that partitions R3 into 2 half spaces. If you do not know what a hyperplane or half space is, please refer to my video on them. I'll put a link to that video in the description section below. This logistic model assigns a probability 1/2 to every point satisfying this equation, and this equation is a hyperplane in R3. So based on the value of A, B, C, D, this logistic model assigns a point on this interval or on this interval to the points on the back of the hyperplane or on the front of the hyperplane. Or it can assign probabilities from this interval to the back of the hyperplane and from this interval to the front of the hyperplane. The takeaway for R3 is that we have a model that has 7 arguments. 4 of them, A, B, C, D, are for creating a hyperplane that partitions R3 into 2 pieces, and the rest of arguments X, Y, and Z represent an input point for the model. Also note that the model is the composition function of this linear term and a sigmoid function. To have a logistic model in Rn, we need a composition function between this linear term and a sigmoid function. We can rewrite it as a function with 2n+1 arguments, where n+1 arguments are parameters to determine a hyperplane in Rn. Also, we can use a shorthand notation for a composition function as this function, which is a composition function of a sigmoid function and this linear term, where boldface A is a vector in Rn and B is a scalar in R, and boldface X is a vector in Rn. And the shorthand notation for the function representation is this function that takes a vector A, vector B to determine a hyperplane in Rn and takes a point in Rn and then assigns a probability to a point X that is in Rn. Well, what did we learn? We learned that a logistic model assigns a probability to each point of Rn, and we realized that every logistic model is characterized by a hyperplane that can be written in this form or in this form as a shorthand notation. And we realized that the hyperplane partitions Rn into two half spaces, and we also learned that a logistic model is a composition function of a sigmoid function and a linear term. That linear term goes to the exponent of e in a logistic model. Also, we learned that a logistic model in Rn needs at most n+1 parameters. And that finishes the video. Thank you for watching my videos, and I hope you've enjoyed this video. There are two things you can do to support me. You can support me by liking my videos and giving them a thumbs up. Also, you can share my videos with anyone who you think would find them useful. Finally, please make sure to subscribe to my channel to get notifications for new videos, and have a great day.